So today we're going to be talking about stress, and there's going to be a little bit of overlap with last week in terms of we're going to look at the Mohr circle again, unfortunately. Okay. There was from last time there was kind of something I want to clear up, and that's kind of how to describe the product of inertia. Okay. So I might just try to explain that concept again. Okay. So again, this is kind of a recap from last week. If you imagine like a steel I-beam, okay, and right now to you guys it might not be like perfectly intuitive as to why, but if you imagine like a gravity load applied to it like this way, it's gonna be bending about its strongest axis, okay, and we call that the x-axis, right? So that's where we get when we do our calculations for moment inertia, we just call that x, right? But yeah, and that's because our product of inertia, when you work out the calculations and do all the balance stuff from last time, so if you remember the quadrants, right? So this section is positive, this is positive, this is negative, right? So it all balances out, right? And it works out to be 0. I'll give you another example, okay? So if you have another shape, so say you have something more like this, which is not too uncommon. It's like a Z-shaped, let's call it a purlin, right? The Z-shaped purlin. What you'll find is that it has more positive than negative, basically, in terms of your product of inertia. Okay. So, with that said, if you apply a force onto it like this, right? It's even though technically the axis that it's going to be bending about is like it's the one that's perpendicular to that force, right? Is the x-axis. You're gonna see that as it deforms and as it bends, it's actually gonna kind of want to do this, right? So it's going down, but it's also kind of warping almost like to the side, okay? And that's because it actually wants to bend about its strongest or like stiffest axis, right? Which let's call that the UU axis, right? So that's because we have a non-zero product of inertia, okay? So the product of inertia is a measure of kind of like whether your shape is going to want to bend straight, okay? That's a very broad way to intuitively understand it, okay? And you know, if we're doing like sideways, right? That's now that's instead your y axis bending, okay? So y. And the transformed one is going to be called the VV axis, which is the equivalent of the y axis and all that, right? So let's just quickly draw the Mohr circle for these two, right? So I'll just duplicate these, okay? So for your inertia Mohr circle, it has to be positive, right? So there's no values of the circle over to the left here. And you'll find that Ix is basically, for the I-beam, Ix is going to be your strongest, or like highest amount of bending resistance, right? So highest moment of inertia. And Iy is your lowest, right? So bending up and down is the strongest for the I-beam, and bending left and right is the weakest for the I-beam, okay? The thing is about when you plot something like this, right, which has a non-zero moment of inertia, is it does actually have a principle being like the highest and lowest bending resistance like kind of point, and that's actually going to be UU and VV, okay? Because like I said, it's going to kind of want to bend that way, right? And the strongest direction that it's bending was this one, right? So actually the biggest, let's call it the principal. So principal is whatever lies on this plane, right? It's principal. That's also principal. Okay, so the principal values are the strongest and weakest in terms of moment of inertia here, okay? And it's also where you get your zero product of inertia. Okay, so this one's IUV. Sorry, like my writing's really cooked because I'm standing up. And so it's like it's hard to write straight. Okay. The other thing is like, do you remember how before I did all that rotation stuff for this one? So I'll just get rid of that for a second. Okay. We established that our product of inertia, IXY, right, was positive. Okay. And so on this axis, it's positive, right? That's your IX and IXY. Some value that's positive, right? You might be thinking, okay, why is that the case for IX and not IY? It's because of the notation. So if instead of XY we write YX, yeah? If we write YX, now we're looking at it from a different perspective. So IX is just the negative version of, IXY is just the negative version of IYX. Does that make sense? But it's whatever is this like leading subscript. So in this case, it's X is the one that's going to be paired up with IX. Do you get what I'm saying? And then same with IY. The leading subscript is going to be, yeah, do you get what I'm saying? The other thing I want to show you, right? Oh, does anyone have any questions about this first before I move on? So something I want to show you from last week is I forgot to point out this formula. It's just here on page 9 of my notes. Okay. So for the principal axes, there's actually a way that you can calculate the principal axis. So this isn't too uncommon of a question in a workshop. It might say like, how many degrees do you have to rotate your shape in like what direction, like clockwise or counterclockwise, before we get to the principal axis. Okay. And so to solve that, you do use this equation. Okay. Yeah. So yes. Okay. I want to point that out because I don't think I pointed that out last time. Okay. All right. So one more thing is, if you remember this shape, right, which wasn't originally bending about its principal axis, remember that the principal axis was here. Let's do it. It's like somewhere here, right? So we're going clockwise. Oh, sorry. Yes, the axis is rotating clockwise. And so that makes sense because we have to rotate that way. So if that's theta p, that's 2 theta p on the Mohr circle to get there. Yep. All right. Okay, so I'm going to move on, but that's like a bit of a recap from last time, and also some things that I didn't fully explain. All right, so we're up to stress this week, and basically, this is. Did you guys do material science first year? I think if you're civil engineering, you have to do it now. But if you're like mech or something, you might do a different course. Or I'm not so sure. But basically, okay. There's a good chance you've heard of this concept before, but I'll explain it properly. So, oh, sorry. Let me just double check I'm clicked onto the right document. Should be that one. Okay, yeah. Okay. So if I have like a material, like a solid object, like this bit of wood, right, and I'm pulling on it, okay, I'm basically imposing a tensile force on it, right, because it's kind of wants to rip the material, like pull the material and rip it apart like that, right? So that's basically what P is, right? P is the force that I'm imposing, right? Tension force. A is the cross-sectional area, okay? And as a result of this, we get a stress inside the material, okay, that develops. And the formula for it is P divided by A, okay? So the stress is just whatever force I did divided by the area. And similarly, I can apply compression force. So if I'm squeezing on this block of wood, or squashing it, I should say, it's imposing a compressive stress, that's what we say. So it's tensile stress, compressive stress, okay? Okay. One thing I want to point out though is the units, basically. So I'm going to teach you this because it's probably going to help you out a lot. in your degree. So these are our SI units, right? And you're probably familiar with them from like high school physics. But generally speaking, they're not really used in structural engineering, at least that commonly. Like you don't really use pascals to describe pressure or stress. You might use it a bit in like water engineering, whatever, if you decide to do that. But what's more common are these other two sets of units, okay? So I'm just going to give them names, which I don't think are the official names, but if you describe this to a structural engineer, they'll know what you're talking about. So let's call this the material properties units or something. And then let's call this the loading units, okay? So what I mean by this is very commonly, if we're talking about material science stuff, or like, yeah, if we're looking at kind of almost like a microscopic scale, right? So like the cross section of like a bit of wood, or the cross section of a steel beam or whatever. Not microscopic, that's not the right word. But yeah, like on a smaller scale, cross sectional scale, we look at the material property units basically, right? And we want to work within this set of units so that we don't get screwed over with our conversions, right? Yeah, so the idea is we typically use newtons, millimeters, and MPa. So what I mean by that is if we apply that formula from before, if we chuck in newtons, right, into P, and we chuck in millimeters squared, we're gonna get MPa returned to us, okay? And it's common to describe materials as being like X amount of MPa strong or whatever, right? So MPa is the units that we use. Okay. Loading units though, typically, if you remember from 1300, right, the loading on a beam is usually described with like kilonewtons, and then like beams are like X meters long, whatever, and you get like kPa loads. So this is the set of units that they would use to describe loading on a building or something, for example, or loading on a bridge, right? You might say like these trucks are going to impose a live load of 10 kPa on this bridge or something. You might just say that, right? That's not too uncommon. All right, makes sense? Okay, so you're going to see this a lot throughout your degree. So just keep in mind, these are two different sets of units, and they're the ones that you're going to want to roll with, basically, so that your numbers are not cooked, essentially. Okay, the other thing to note is that P, sometimes you'll see this as F, right? Sometimes you'll see it as N for axial force. Yeah, as long as you know what you're talking about, this is just the tensile or compressive force that we're describing here. And that results in your normal stress. Normal / sometimes called axial stress. Yeah, makes sense? Okay. Okay, so next, shear stress is a little bit hard to describe, but I'll try my best. So imagine I have two bits of wood, okay, like what I've got here, and I've glued them together, right? And now I'm pulling, like, I'm applying a tensile force on the ends of these bits of wood, right? So I'm pulling it out, okay? So even though I'm applying like what would be a tensile force on the members, okay, what happens is that the glue interface, right, the interface between the two bits of wood is actually experiencing shear, right? Because these want to slide off each other now. So on that glue interface, it's actually experiencing shear force. Does that make sense? Okay. So even though this is P for the bit of wood, from the perspective of the bit of glue, it's in shear, okay? And to get your shear stress, which is indicated by this Greek letter tau, you do your shear force, divided by your shear area. Sometimes you might call it AV, or you might call it A, or sometimes I've seen it as AS, right? Doesn't really matter as long as you know what we're talking about. We're talking about that area of glue, okay? Make sense? Yeah? Okay. So something that comes up decently often in like the workshop questions in this course is, imagine, like, what's pretty common to connect like 2 bits of wood, for example, or 2 bits of steel is some kind of dowel, right? That's like a pretty general term. But it's basically a connection. So like to attach any 2 bits of material like steel or timber, you need some form of connection. Okay, so that might be in the form of a screw, a nail, bolt. In the question later, you'll see it called as a pin, right? Or something else. But it's essentially acting as a dowel. So dowel takes on shear force, right? So as this as we're applying this tensile force onto the bit of wood, the connections basically wants to like slice in half, right? So that shear force that's induced is basically taken as shear stress by the connection. Does that make sense? By the joint. So that's what's called a single shear joint. Okay. So something else I want to talk about now is like, okay, that might raise the question: why is it a single shear joint? Is there a double shear joint? Okay. So if you imagine the wood again. Except now there's 3 layers of wood, or 3 planks of wood. By the way, have you guys seen a line break before? You might have seen this, or you might not have seen this, but this is like super common in like engineering drawings, which is what we in Australia called blueprints, basically. So in engineering drawings, you'll see this thing. Looks like that. And it means that's the end of my drawing. That's it, but it keeps going. Do you know what I mean? So it's to indicate that this it doesn't become a floating mess off the screen. You know, you might do, for example, and this is like a stylistic choice. It's a little bit of an art. You might do like 2 line breaks there, but like the material we're talking about is like here, here, and here. Anyway, that's the line break. Okay, so imagine we have a dowel that runs through it like that. So before it was what we call a single shear plane. That's 1 shear plane, right? And it's 2 bits of material. How many shear planes do we have here, assuming that we have our force pulling on it again? How many shear planes do we have? Exactly. We have 2 shear planes, right? It's the 2 interfaces. So that would be a double shear joint. Is that what it's called? Yeah, a double shear joint. Okay, does that all make sense, Jaron? Yeah? Okay. Does anyone have any questions? Okay. So, alright, here's where it gets a bit stupid. So basically, I'm going to try to explain something called factor of safety, which is like a general engineering concept. But I'm going to try to explain it in an analogy that is like basically how I understood it, okay? So if you think of like a video game, right, basically, HB bar is like how much health or whatever your character has, right? And then they might get hit by like a club or something. I don't know. And then they're taking damage, basically, right? So this analogy is what I want you to think about carrying over to a building or a structure or whatever. Okay. Each building has a certain capacity, right, which you can work out, which is like its health bar, basically equivalent, right? And then the loading that's on it. So maybe you stack cars onto that building, whatever. That loading is the damage. Okay. So I want you to think about these numbers from that point of view, right? Not just as numbers, because basically, okay, I'll explain the factor of safety in a second, but yeah, I just want you to clearly understand that these are 2 different things: loads and capacity, right? So the external force that we are applying, right? So for example, on this bit of wood, me pulling the wood apart, right? That's the damage, right? That's the load, right? And you can normalize that into a stress, right? So whatever force that I'm applying, divide it over the wood's cross section, and that gives you the amount of stress that's being applied on that bit of wood. Do you know what I mean? Like the normal stress. Okay. The failure stress is usually what's going to be given in the question in this class, and it just tells you the max amount of stress it can take before it breaks. Okay, so that's the equivalent of like your health bar or whatever, right? In my stupid analogy. Does that make sense? Okay. All right, so here's where it gets interesting. So factor of safety, this is basically a way for engineers to add like a factor of safety. Okay, so what that means is imagine you're playing a game, right, and your hero is taking damage, right? Okay, so your hero's taking damage, but your hero's like has to account for it, right? So we'll do a factor of safety of 2, right? If your hero has 100 HP, right? You're like, okay, if I take 50 damage, I'm already too deep to stop this analogy. Okay, so just bear with me, please. Right? So if I take 50 damage, I'm like, okay, I'm going to go back to my base and I'm going to recover. Okay. So that's what the factor of safety is, right? Factor of safety of 2 means once I reach half HP, I want to go back to my base and I want to recover. Okay. That's what the factor of safety is. It's a safety factor because it's like that's how much you want to exaggerate your load or your damage so that it never reaches the point of breaking, or in this case, your hero never dies. Okay, kind of makes sense. Do you see how I cooked there? Okay, thank you. All right. So that's what safe and unsafe is, right? In the context of structures. Okay. All right. So I'm going to go through 2 examples today. I'll go through this first example, and hopefully you understand what I'm talking about there. And then we'll take a break, and then we'll go through the second example after I explain what like the transformation stuff is. Okay. So let's just bear with me. Let's do the first example first. Okay. Okay. So there's a rigid bar AB, and it's supported by a steel rod on the left, and a roller support on the right. And the steel rod, this thing, has a diameter of 20 mil, okay? And there's an aluminium, sorry, block having a cross-sectional area, so that's that thing. It doesn't really say the shape, but whatever, it doesn't matter. Let's just pretend it's rectangular. It has a cross-sectional area of 1800. That's that. And then also, we have pins at A and C, and they're subject to single shear. So, what's the best way to look at this? Okay, pretend I'm looking at it side on like that. Okay. What would probably be happening is that's it's kind of dumb. That's your hanger thing, which is the thing at the back there, and then maybe that's your aluminium block, right? And then maybe that like continues down, right? And your pin is in single shear, like that. So the pin is the connection thing, basically, right? So that cross-sectional area, oh sorry, it doesn't say the cross-sectional area, but it's saying the diameter is 18 mil. Okay. So I'm getting some confused looks, but I wanna take the time to explain all the elements here. Sorry, that's blue beam. Okay. So we got 3 things, right? We got the rod, the hanger rod. We have the aluminium block, right, which has a certain cross section, okay, which was 1800. Yeah. And then we have the pin, which is the connection, and that has this diameter, 18 mil diameter, and it's in single shear. Yeah. Okay. So those are our 3 things that we have to check for, right? And the first thing that breaks, okay, imagine you had like 3 chains, okay, and you're pulling on it, right? And these chains are made of different materials and they have different cross sections or whatever. The whole thing's gonna break once the first chain breaks. Do you know what I'm saying? And that's basically what our system is. It's like a series of chain links. So whatever breaks first is gonna govern like what's gonna cause the whole system to fail, right? Okay, So it gives us our failure values, or how much stress that each one of those things can take. So for steel, it's 680. For aluminium, it's 70. And for shear, it's 900. Oh, sorry, for the pin. Sorry, for the pin, it's 900 MPa. Okay, but they also have different cross-sectional areas, so we have to basically check everything. Okay, but firstly, let's find the forces, right? Let's find the forces. So the question is basically telling us determine the largest force P, or like load P, that's applied here, right, in the middle of that the rigid bar, which is effectively acting like a beam. Okay. What's the biggest value of P before this whole thing breaks? And then apply a factor of safety of 2. Yeah? Okay, so like basically we don't know what the reaction. Okay, so if you imagine a beam like that, right? And I've got a force on it, okay? We have these reactions, right, if you remember from 1300. Let's just call it AY and AB, BY, okay? Right? Let's just pretend that this is 1 kilonewton, okay? So if it's right in the middle, right, how is it divided into your reactions? Half and half, right? That kind of makes sense, right, intuitively, right? So if I have like a ruler, and I wish I brought it. No, this isn't gonna work, is it? Okay. I'll give up. Okay, so basically, okay, I'll draw it as if I brought it. So imagine I had a ruler, right, and I stick my fingers here, right? This one's my fingers, that's my fingernail, okay? And then someone like jumped on it in the middle, okay? Right? The fingers are gonna like hurt an even amount. Do you know what I mean? Okay, what if like someone jumps in it over here on the towards the left? Which finger's gonna hurt more? A or B? A, right? So this one's gonna take more of that load. Does that make sense? Right? But obviously we can figure it out based on like 1300. But like that's what you should be able to like think about. So how much like my finger hurts is called the reaction. That's what I'm trying to get at, okay? So that was like a long-winded explanation to say, let's figure out the reaction. Right, because that's a support and that's a support, right? We have to figure out, okay, what's the AY here, right? And that reaction is the force that travels into this system that we have on the left. Does that make sense? Okay. Okay. All right. So find the reaction at A using static equilibrium. So jumping back to 1300. Basically, right, if you guys, because when I did 1300, I think it was during COVID, and I think I used Chegg, so I don't remember much from it from back then. So let me teach you it from the basics, basically, right? So the way it works is when you're taking a moment, right? Oh, sorry. Let's pretend we know what the force is, right? How many unknowns do we have other than that force? We have 2, okay? I'm gonna draw something called a line of action, right? So that's as if those reactions extended infinitely in both directions, up and down, okay? So that's our line of action, okay? So basically, when we're doing our moment equation, right, which is very basic, right, we have force times lever arm, okay? And we have 2 unknowns, right? We have the reaction at A and we have the reaction at B. There's a cheat that we can do in order to make it so that there's only one unknown in the equation. And that's setting the lever arm of one of them to 0. Does that make sense? So if I take, because I can choose to take the sum of the moments anywhere along this beam. I can choose it here, I can choose it here, whatever. But if I do it there, I'm going to end up with 2 unknowns. So there's only 2 spots I can actually choose where to take the reaction in order to eliminate one of our unknowns. Right? Do you guys know where that is? So if I choose to take the moment at A, right, I'm going to end up finding the reaction at B, because the other one has a lever arm of 0. Does that make sense? But if I take some of the moments at B, the other thing happens, right? If I take some of the moments at B, you end up finding A. So that's how you have to choose like what you do, right? Okay. So with that said, let's let me open my notes 1 second. How much time do we have? Okay, we have time. Okay, let's take it. Let's take some of the moments at B. Okay, and we set it to be 0, right? Because the whole system's static, which means nothing's moving, right? There's no like constant acceleration. Oh, sorry, there's no acceleration basically on our system, right? So we take some of the moments is equal to 0, and so we're like, from our point of view, it's over here, right? And so it's like we have this force here, and the lever arm is 2, okay? Because we're doing that, and then we also have this force here, and the lever arm is 1.25, right? Oh, sorry, and we're going, when we go clockwise, right? So for RA, it's going to be negative, right? So that's the lever arm, -2. Oh, sorry, -2. Ah, fuck. RA, and 1.25 P. Yeah, does this ring a bell? Okay, cool. All right, so let's solve it in terms of RA. Okay, so we get this like expression or whatever, right? Which I know it's like has like an algebraic value in it, but we're just going to carry on with it, and it'll make sense in the next steps, like how we're going to solve for P, basically, right? So going back to my finger thing, right? Basically, because our force is slightly to the left, right? So it's not quite in the middle, because that's the middle, right? What it's saying is 62.5% of the force coming down from P goes into the reaction on the left, right? Whereas I can't be bothered to do the maths. The remainder goes into the one on the right. Does that make sense? So that's why we can't directly just put P in for our force in this workshop, this question, right? Yeah. Okay. All right. So this is given in the question, right? We know that the amount of stress before failure in the steel is 680 MPa. We know that the amount of stress in the aluminium before it fails is 70 MPa, and we know that the amount of stress, specifically shear stress, in the pin is gonna be 900. Yeah, I think about it like this, right? By the way, that's the rod, and the force is traveling that way, right? So that's 0.25 P. Yeah, it goes into the aluminium block, right? So that's the aluminium block. That's the rod, the steel rod. And then that's connected to a pin. Right, so that's just like a reaction. That's like a support. That's the pin. Yeah. So in purple's the pin, and then now that's taking shear. Right. So that's axial, right? So that's normal. It's called axial loading. That's the aluminium block is taking axial loading, but the pin is taking shear. The connection is taking shear. Do you know what I mean? So that's what I mean by this is like a series of chains that are linked together. And the first one that breaks. Okay. All right. Okay. So that's that. All right. Next is applied area. Let's see if my laptop's left. All right, so we know that the steel rod was a rod. So we have a formula for the area based on diameter. right? So if you remember from high school, the way that I learned it was pi r squared or whatever. Pi r squared is the same as pi on 4d squared, because when you sub in d on 2 for r, right, you get the one on the right instead, okay? So we're doing it in terms of diameter. Oh, sorry, I know before I did phi for diameter. Sometimes you see diameter as like capital D or like lowercase d. Sometimes you see it as phi. But that's the one that's going to be 18 mils, just mil. Okay? And that equals whatever. The aluminium was just given to you as a cross-sectional area. And then the pin was also pi on 4d squared because it was like a circular cross-section as well. Wait, am I done? Possibly. It was 20, wasn't it? I was just testing you guys. All right, so that one was the one that was 20. Okay, that makes more sense. So the one at the top was 20, and then the other one was 18. Okay. All right, so that's all the areas. So we've just collected like all the numbers that we need, and we're gonna plug them in, okay? Okay. Sorry if you're still writing. I'll come back to that if you need to still write it down. Okay, so basically we're gonna sub everything in, right? Because we know this is our equation, right? It's an inequality. Like we have to apply a factor of safety to your loading and make sure that the amount of load is less than the capacity, right? Because capacity is absolute max before failure. That's your HP bar, right? And the load is the damage, right? So yeah. All right, so that was 2. The applied loading, remember we were given a force and we were given an area, right? So we convert that to a stress by dividing it by each other. So the force was this, right, in terms of newtons. And the area for the steel was this, yeah? And we were given that the failure MPa capacity was 680, right? All right, so you can kind of see where this is going. If you solve it algebraically, right, we're gonna solve for P. You get that it is equal to this, okay? So this is in newtons. Now this seems a bit weird because when you're talking about loading, usually you talk about it in terms of kilonewtons, right? So if you remember back in 1300, everything's like kilonewtons and meters. So we're just gonna convert it, okay? So we had things in terms of MPa and remember that set of units I was talking about, right? We had MPa, newtons, and millimeters, yeah? So like that's how I know that we're gonna get newtons when we chucked in something that was MPa and millimeters. Okay. But all we have to do to turn newtons into kilonewtons is divide by 1,000. Right? That's the answer. Okay. Okay. And then basically similar idea so now we're talking about the aluminium block, right? So we have the same force that's going through the whole system, right? This is traveling from one link to another, okay? So it's the same force, right? So if I had the 3 links and I'm pulling on it, right? It's the same amount of force that's traveling through all of them, but they might be experiencing different stress levels because the cross-sectional area of these like links or whatever could be different. Does that make sense? Okay. Okay. So the area of that was 1800, right? And the failure MPa was 70. Make sense? All right, so now we're gonna solve for P again, and we get 100.8. And similar idea for this, except the area was this. And we had a different capacity MPa on the right. All right, so based on these 3 numbers, 170, 100, and 180, right? Which one's gonna fail first? The second one, right? Yeah, because now we've kind of like we've standardized them all into a force, right? So we know that okay, basically that's your HP bar. Okay, so we don't know what the HP is, right? And you accumulate a certain amount, and the one that fails first, which is 100, is gonna break, and then it keeps going, and then it's like 170, and then that one's like 183 or whatever, right? Do you know what I mean? So the one that's the lowest is gonna be the one that breaks. Yeah. Okay. All right. I'll give you guys a break. And we'll talk about transformation. So we'll be back in like 5 minutes. All right. Let's get back to it. Hopefully we can finish before 11. All right. Okay. So generally, I reckon the Mohr circle is like a pretty hard concept to explain. A lot of the questions that the students who came up front here to ask me were about last week's Mohr circle thing, and there's no quick way to explain it, unfortunately. But yeah, you're gonna see it for these next few weeks. I'm sorry. Okay, so back to the Mohr circle. Sorry, back to a 3D stress element, right? Basically, if you have what's a good example? Okay, pretend you have the tension rod or whatever that we were talking about before, right? So if you imagine this is made out of steel, and you imagine that you're a tiny bit of steel in this rod, okay? Basically, you're experiencing something called uniaxial stress, right? Which means only in one direction. You're getting pulled in tension, okay? But if for whatever reason this rod also got stretched sideways, right? Now you're doing biaxial stress, but then also into the page, arrows, right? Now it's triaxial, okay? So there's 3 dimensions you have to consider, right? So that's a 3D stress element. But that's just the what's the word? The normal stress component of it, right? But I'll just explain that for now. And this is outside the scope of the course, and just to let you know this exists, but you can plot this kind of triple circle situation for triaxial stress, but we're not gonna do that, which is great. What we're gonna do is we're gonna just focus on a 2D stress element, right? So let's ignore the dimension going into the page, basically. Right, we're just gonna focus on the 2 dimensions, right? And the shear that's being induced on it as well, okay? So I'll give you some examples, right? But basically, one thing to note that's different from this week and last week is on this Mohr circle, instead of your moment of inertia in the X or Y direction, or U or V or whatever, instead of moment of inertia being plotted on the x-axis, you have stress, you have normal stress, sorry. And instead of your product of inertia being plotted on the y-axis, it's your shear stress now, okay? The other thing is you can have a positive or a negative axial stress, right? So we just take one direction as positive. So for the example of something being pulled in tension, like this tension rod, we'll just say the tension direction is positive, okay? So if it's experiencing 100 MPa of stress in tension, it'll be positive 100. Or if it's experiencing 1 MPa, let's say, 1 MPa of compression, it'll be negative 1 MPa or whatever, right? Does that make sense? So yeah, all of a sudden, our Mohr circle, we're gonna plot so that there could be negative numbers on it as well, okay? All right, let's give you some examples, right? So yeah, if we have a stress element, a 2D stress element, and it's experiencing that uniaxial tension, let's say, the Mohr circle is gonna look like this, right? Okay, so why do I mean that? It's because we're just focusing on the x direction, okay, and the x direction is getting pulled and it's non-zero, right? But nothing's happening in the y direction. Okay, so up and down is 0, and therefore we plot the y point on the small circle at 0. Okay, and then you draw a circle that kind of connects both of them. Right. Okay, what happens in compression? Basically, if we're taking compression as going left on this graph, right, on the Mohr circle graph, it's going to be plotted like this, right? So again, there's 0 y direction force or stress or whatever. Okay. And so we can just plot it as at 0 and then the negative number and then connect the circle. Yep.
Is this about like a slice as you rotate the block? Does that make sense? So you have two points acting like that, and you have a cut like that, and you're going, what's the normal for the shear?
Yeah,
As you rotate the block with the same cut, cut's going to be on an angle.
yeah, that's a good question.
Kind of right.
Yeah, so yes, it's looking at it, so it's not a cross section, because cross section would be perpendicular. So you're right.
Yeah,
it's looking at it. Yeah.
Yeah.
Yeah. Yeah. Okay, so here's one which is like general tension, right? That's plotted, and that's where that 2D stress element's being pulled, but in the x and the y direction. Okay, and then in this particular scenario, it just says min or max. I think I didn't specify which one's getting pulled more, but let's just say this one's getting pulled at 2 MPa, and this one's getting pulled at 1 MPa, right? That'd be your 1. I know it's not like, I'm just making these numbers up, right? So it's not like plotted accurately. But yeah, you'd have something like this, okay? So the other one's non-zero as well. So both are non-zero values, right? Okay. The other one's compression, right? Similar idea, so that's general compression. Okay. All right, shear. So it's a good way to explain this. I didn't think about this explanation that well. Okay, think of it like, let's have the blocks of wood again. So this is one block of wood. That's another block of wood, okay? It's being pulled, right? That's your shear plane. And then imagine you're a tiny bit of wood that's plotted like that, flat on the shear plane. Okay, so that's when you would have your shear essentially. Okay, and that's when you're plotting up and down like this. Okay, so that's pure shear, right? And then you can also have tension and compression and whatever, right? If you get tension and compression, your Mohr circle is going to cross over into like both the positive and the negative plotting regions, right? Okay, all right. So does that kind of make sense? All right. So there's a bunch of formulas again, just like last week, but they look pretty similar. That's the good news. So we can rotate our stress element just like how we could rotate our cross-sectional shape from last week, right? And we can apply all these formulas, and they were based on trigonometry, the simplification thing, right? The trig identities. Yeah, that's the word I was looking for. Okay. The only one that I will talk about that I forgot to talk about last week, I guess, is I didn't really tell you. It was on my notes, but I didn't point it out when I was talking. The angle to the principal plane. We actually have a formula for it, right? So yeah. Basically, you just apply this and make sure your calculator is set to degrees. And you can plug in these values, and you'll get how much it needs to be rotated to get to the principal plane. Okay. Okay. So it'll make more sense once we look at the example that I've got lined up. Okay. All right. Yeah. So that's basically, imagine your Mohr circle looks like this, and you're given these values here, which are your rotated ones. Is that the rotated? Yeah. you're given these ones, right? To find the minimum and maximum, sometimes they're called x1 and x2 or 3. Basically, 3 comes from, do you remember how I said there's like the other version of the Mohr circle, which has like the triaxial plotting, right? It would be, the notation comes from, this is 3, this middle one's 2, and then this biggest one's 1, right? But how the formulas translate over is sometimes people call the smaller one 2, and sometimes call it 3 once it's translated to a Mohr circle that only has one circle, right? So for this point here, yeah. Okay. Again, formulas, very similar to last week, but yeah, there's ways to find the middle of the circle, and there's ways to find that radius that the circle's, so radius of the circle, right? Okay. Okay. For some reason, I've just had a feeling that I'm not recording. Okay, I'm recording. All right. Okay. So here's a question. It's in the workshops. I actually didn't paste all the text, but there's like a full paragraph describing it. It's like, here's the stress element for some material, and the material has like these, I guess, like bedding planes or whatever. And these so this is orientated at 30 degrees from the horizontal. Oh, sorry, it's not bedding planes. It's called it's some linear elastic material, and it's got laminates or whatever, right? This is what is in the question. Okay. So it gave us all these values, right? So they conducted this biaxial test, and this was like the response basically, right? We got 2 MPa in tension in the x direction. We have 1 MPa in compression in the y direction, and the shear was negative 0.5 MPa. Okay, so the first part of the question, I probably should just paste the question here, to be honest. The first part of the question just said, what are the values for the transformed stress once you rotate it 30 degrees? Okay, so we're just going to plug in those numbers, right? So it's literally, you sub in 2 MPa and negative 1 for x and y respectively, and negative 0.5, right, for the shear, right? These values will pretty much always be given in the question, I think. Yeah, I don't think you ever really have to rearrange this equation. Yeah. So yeah, you plug it in the way that you see it here, basically, every time. One sec, I'm just gonna get up my notes again. Okay. All right, sorry about that. Okay, so the value you get when you punch in the calculator is 0.817 MPa, right? So this is the transformed stress in the x direction. Yeah, because we've basically, so if that's our stress element, right? And we had those planes with the laminates orientated at 30 degrees, right? Before we had x and y going this way. But now it's saying as if we're doing this in the same direction as those laminates, right? And now we're pulling this way, which is the dash x axis, and then this way, which is the dash y axis, right? Right? So that's kind of what the question's like, asking you to calculate, I guess. All right. Yeah, similar idea for y. And we get this, right? And similar for shear stress. All right. So one thing to keep in mind, like when you're doing these formulas, right? They can look pretty samey. Just want you to be careful about these parts of the formula. That's a bad color to. All right. Okay, that's more contrast. Do you see where I've highlighted in red and in purple, right? So just keep, like when you're writing out the formula, just make sure you have those signs correct, because that's a very easy place to make a mistake. Okay. All right. I can see people still copying. I'm just gonna give it a second. Yeah. Oh, the other thing I forgot to mention is when you have a stress element, right? Like basically there's typical positive and negative directions. So going away from this 2D stress element is positive, right, in tension. And going in is compression, right? So that would be a negative value. But what's less intuitive is the direction that you'd notate for shear stress. So going up and right into that corner, that's positive. And down and left, so that's the positive convention for shear stress. The negative would be the opposite, basically. So that's the negative convention for shear stress. Okay? Yeah. All right, I think there's enough time to move on. All right, so principal stresses. So when you hear the term principal stresses, is this referring to, like on the Mohr circle? Let's just draw like this, okay? Here and here, right? Yeah? So it's just the minimum maximum value. Here, this is called the principal, right? The principal stresses. Sometimes this is called stress 2. Right. All right. But yeah, this is like you can either do it as 2 equations or you can just do plus or minus, right? The plus is always the one that goes this way. Yes. So the plus is always the one that shifts you to the right, and the minus is always the one that shifts you to the left, right? So the minus will be the smaller, will be the sigma 2. All right. And that gives us 2.08 and negative 1.08. All right, so if we're thinking about this in terms of your Mohr circle, that's this one, and that's this one, right? We'll plot it all together in a second. This would be an MPA. Okay. All right. I'll mute these. I'll just go busy. I think that's gonna stop showing those notifications. Okay, makes sense? All right. Oh no. Wait. Notification settings. Do not disturb. Okay, I think that should work now. All right. So principal orientation. So this is the one that we didn't really cover last week, but basically there's a formula that's similar from last week. You just plug this in, okay? And then once we just quickly solve this fraction, we get negative 1/3. All right. So now like we do. Oops. So there's tan 2 theta p, negative 1/3, okay? And so remember that tan is like a function and it captures everything in that bracket, right? So what we have to do first is we have to do tan to the minus 1, like that, right? But then if we want the just theta p by itself, then we can divide it out. Do you know what I mean? Right. So just be careful with how you're doing these operations on your calculator, because this is another point where people can make mistakes. Right. All right. So let's see how it all plays out. So again, I mentioned your principal axis, right? That's probably the easiest one to understand. And in terms of how to plot, right? It's where we have 0 shear stress, and then we had these values. Okay, so that's the 2.08 number that we looked at before. And this was negative 4.08 and 0. So that's from this equation, remember. Okay, so that's plotted on the flat line. All right, next we have the xy plane. By the way, just because like in a stress element, right? Just because we're shown a stress element and we're told that this is x and this is y, and this is y, doesn't necessarily mean it's the principal stress. Do you know what I mean? Because before we were looking at like I-beams and stuff, right? And then from an I-beam you were like, okay, well, we know that an I-beam bending about its x axis is the strongest direction, right? And so therefore the IX was actually the principal plane. That's not the case necessarily. So when you're looking at a 2D stress element, right, you can't trust that this perfectly lies on our principal stress plane. Okay? So what I mean by that, or there's a way to check actually, by the way. But what I mean by that is we can actually plot our XY plane as well. And the way we do that is if we look at these original values, okay? I'm just going to paste this in, right? These are our original values. Okay. And we know that x is in the positive, right? So this is the 0 value, and then x is somewhere here. It's somewhere to the right of 0, okay? So let's just plot it here, right? So this one is that, which is 2, okay? So it's just under 2.08, right? Which is our principal stress. But how do I know that it's under? How do I know that it's lower? It's because the shear stress that we're given in this question is negative 0.05. Do you get what I'm saying? So negative 0.05 is under y equals 0. Do you know what I mean? It's under. So it has to, like on the Mohr circle, it has to be a point that's this way. Do you know what I mean? Okay, so you might be wondering like, okay, how the hell am I supposed to know it's paired with that one and not xy? Oh, sorry, not sigma y, right? And the reason, let me just plot sigma y real quick. Because this one was negative 1, right? The reason is it's flipped, right? So instead of negative 0.05, negative 0.5, it's just 0.5. But we call this something else, right? We call this value, instead of tau xy, this one's called tau yx. And this isn't conventional to list out in a question, right? So tau yx is the one that's paired with sigma y, okay? But tau xy is the one that's paired with sigma x. Does that make sense? So that's kind of the logic you have to work through in your head. Okay. Now the other one is the bonding plane, right? So the bonding plane was when we have those layers, those laminate layers, and it's like the bond or whatever. That's plotted somewhere else. So let's get those values. All right, I'm going to delete these ones. That's x, that's y, and that's this one. Okay, give me 1 second. That's x, that's y, that's this one. Okay. I'm just going to rewrite these variable names as well. Okay, so how would we plot this, right? The first thing you do is you look at x, right? So you look at the sigma x dash, and it's to the right of x equals 0, okay? So we know that it's somewhere here. Okay. Next thing we look at is whether it's negative or positive for tau xy. And we see that's negative. All right. So we're going to be like, all right, it's here somewhere. So this one is sigma x dash, which is 0.817, and it's also tau x dash y dash, which is negative 1.549. Okay. Over here, over here we have the other one, which remember is a positive number, so it can't be over here. It has to be a positive number over here. 0.183, and tau yx dash dash is the positive version of it. Okay? Okay. Let's do it in purple. I don't know what I'm cooking with these highlights, but yeah. Does that make sense? So you see how all the numbers like fall into place? So that's how we do these kind of questions. Right. So that's the end of my workshop. Thanks for coming, and I'll see you guys next week. And if you have questions, which I know a few students have had, just come up front, particularly about last week or whatever.